Well, thank you everyone for coming into the seminar. So it's a great pleasure to introduce Santo Fortunato. So he's currently serving as a director of the Indiana University Network Science Institute, and he's a professor at the Ludi School of Informatics, Computing, and Engineering. So before joining the university, the Indiana University, so he was previously professor of complex systems at the Department of Computer Science at Aalto University in Finland. And as an anecdote, so he's the first individual who was promoted to the rank of full professor at that university. It's a relatively new university, and Santo made the history books on the university by becoming the first full professor they promoted. Professor Fortunato, so he received his PhD in theoretical particle physics at the University of Bielefeld in Germany. His doctoral research was on lattice gauge theory, percolation, and phenomenology of heavy iron collisions. And then he decided that he wanted to do a career change, and he moved to the field of complex systems, pursuing a postdoctoral appointment at the Ludi School of Informatics, Computing, and Engineering at Indiana University. His primary mentor was Alessandro Vespignani, and I served as his co-mentor during his postdoctoral fellowship. And he did an outstanding job. I learned tremendously from him, so it was a great pleasure having served as his co-mentor. So in fact, I think I was his co-mentor. It was the other way around. And when he made his transition as an independent scientist by moving from Indiana University to the Institute for Scientific Interchange in Turin, where he was a scientific leader. And those of you who do not know much about that institute, that's an elite research institute in Europe that actually focus on complex systems and network science. And when we were chatting about his career transition, so Santo explained me that he wanted to actually move into the physics of social sciences. And that was the reason he wanted to pursue an independent career, because in the subjects Vespignani and I were working on were not on that area, were more on the biomedical sciences. And his current research focus is on network science, especially community detection graphs, computational social sciences, science of science, and climate change. And Santos, so he's a really start in the field. He has published a large number of papers in Nature Science, the Proceedings of the National Academy of Sciences, Physical Review Letters, reviews of modern physics, Physics Review, and he has collected over 33,000 citations when you look at his Google Scholar profile. His review article on community detection in graph that was published in Physics Reports in 2010 has accumulated a large number of citations and is presently considered the best and the most highly cited paper in network science. He has been recognized by a number of awards. He's not only an incredibly well-funded scientist, he currently holds 2 major network science grants, one for $2 million from the National Science Foundation, and one of $5 million. That is a large international grant. But as well, he's a recipient of the John Scientific Award on Social and Economic Physics from 2011, a prize that is given by the German Physics Society for his astounding contributions to the physics of social systems. He's serving as the founding chair of the International Conference for Computational Social Sciences and the chair of Networks 2021, which is the first merger of NetScience and the Sub-Belt Conference, and it's possibly going to be the largest event in network science that people have experienced. So if you like to enjoy a really good conference, I just encourage you to attend. And with that introduction, I think it's now time that you start to listen to the real expert, which is Santo. And I'm very grateful you accepted to come and give the talk.
Thanks, Santiago. I mean, after such a nice introduction that I'm really flattered about, the best thing I could do is probably really just to leave, because I think anything I can do can only spoil this great things you just said. I try to do my best. One thing Santiago didn't say is that we are very good friends. We also play soccer. When we were here, I was actually organizing the weekly soccer game, and you would occasionally show up, play, with other faculty and so on. It was happy times. It was when I started my adventure as complex system scientist full time. And like he said, I was a postdoc mentored by 2 sponsors. Alessandro Vespignani was the one that I originally interacted with before I moved from Europe to here. And then when I was here, I was technically put on a grant that was also involving Santiago. So I was attending his lab meetings. We had unfortunately only one paper together, which also stirs some debate, as you know. Somehow wasn't really,
oh yeah, that was a good debate.
Yeah, somehow it was kind of a bit discouraging, saying, "Oh my God, my first trip towards biological systems." That's perhaps why I stick to social systems ever since. Now it's not true, actually. I also had other experiences, and now I met so many nice people in the area. So I'm pleased to talk to you about this. I had to, deciding what we had to talk about. I mean, I have various interests, but probably I'm best known certainly in network science for community detection. I thought the best service I could provide to your community was to talk about this. And rather than focusing on the latest things I've done here, I decided to go through some of the highlights of my main contributions in this area, which are still kind of presently used and by a lot of people, and hopefully will influence also future developments in this area. Let's see. So with your permission, I'm going to share the screen now and start the presentation. So let me see. This is where we are, and let me start the slideshow from this page. Yeah, so here we go. Let me see if I can make this smaller. Perfect. I hope we can see everything. So this is a talk about something which is known in various disciplines under different names: community detection in networks, community discovery, some people in computer science, graph clustering or network clustering by other people in network science. So I will refer to that. And precisely, let me formulate the problem, is to basically breaking down a network into some fundamental organizational units. Like for instance, in this case, we have this very schematic network, and you can tell that there are groups of nodes which like each other because of their clearly higher edge density, more than they like the other nodes. So the connection between the nodes of different groups are indicated by these green lines. Otherwise, you have these black lines, and the ovals enclose these groups of nodes. So these are what you call communities or modules or clusters. I can use one of these three terms during the talk. The meaning is the same. This is not the only way to define groups. This is the most dominant interpretation of the term and utilization of the term, the so-called assortative community, in which we really have this high density of links inside and sparse connectivity between the groups. There are also other ways other types of groups, but I'm not going to deal with that today. Speaking about what these groups represent in networks that you are familiar with, you can think of them as social circles in networks of social interaction, social networks, or scholars working on the same field in collaboration, co-authorship networks, proteins with equal similar function, in biological systems, but also metabolic networks, so groups of metabolites involved in similar processes, papers on the same related topics in citation networks between documents, and so on. You can make a lot of examples. And why would we care about these groups at all? There are several reasons. The organizational reason. You want to know how the system is organized. It can also help you to better uncover properties of the nodes based on their position within their groups. For instance, you can distinguish nodes like this, which are fully embedded in their groups. They don't really share any, connection with any other node outside of the group, as opposed to these other ones, which are so-called, gatekeepers, that in fact keep this group here connected to the rest of the system via their links with other nodes, the nodes of the other groups. You can also investigate the effect on dynamics, for instance, how important it is, the modular structure for process, especially, I don't know, specifically spreading process, epidemics, information. We can help to address the problem of missing links, which is a really traditional problem. It's becoming more and more important now. I could give more examples. And I hope that overall this convinces you that this is a big problem. In fact, it is the most popular topic within network science. By looking at the number of citations received by papers in this topic, you will see that no other topic within network sciences receive more attention because it's methodology. It's a basic methodology that you can use and apply in a variety of different contexts. But it is a difficult problem. Among the other things, it's an unsupervised classification problem. As such, it is then ill-defined, which means, which in a sense contributed to the popularity of this topic because everybody felt, that he or she had to say something about it. Not always that led to improvements or progresses of the state of the art, but sometimes it did. And so we are happy about all these contributions. What this problem looks like could be summarized by this exercise that I'm doing. This is the adjacency matrix of this network here. Adjacency matrix is a matrix whose elements are, for undirected and weighted networks like this one, is a matrix that tells you which nodes are connected to each other. The ones here indicate which nodes identified by the 15 labels here. There are 15 nodes here are connected to each other. And the empty space, I could have put zeros, but there would have been so many zeros. I prefer to put just, to leave them blank, indicates the absence of a link between the corresponding label nodes. Finding communities essentially means to operate a transformation of this matrix that leads to an approximately block diagonal structure like this. So if I rearrange what I did going from the left to the right, I just rearrange the labels of the nodes by putting first the labels of the nodes corresponding to the red nodes, and then the blue nodes, and then the yellow nodes at the end. And you see, if I'm doing that, I see that there are many more. I can really see visually by inspecting the matrix, the rearranged matrix, that there are many more links inside connecting the red nodes to each other, or the blue nodes to each other, or the yellow nodes to each other. Then there are links indicated in this case by these green ones connecting nodes of different groups. So this is a way that tells us, that there are some groups, there is a community structure in the system, which was not obvious by inspecting the original matrix. Of course, that's a simple exercise. In this case, it's a 15 by 15 matrix system with 50 nodes. Imagine how complicated this thing is if you analyze a network of millions or tens of millions of nodes. It is an ill-defined problem. The main question is, what is a community? How to define operational community? What's the concept underneath? There is this general, very high-level concept of having high density of edges inside and a relatively lower edge density between the groups. But this very same, very high-level concept can be formalized in many, many different ways. And then the other thing is that once I define a community and I find a group in my system, is there a way that I can assess its significance or strength, how good that group or partition actually is? So these are exactly the questions around that generated this entropy of methods that have been proposed over the last 20 years to address this problem. So this is the outline of my talk. I'm going to focus on three things. My first somehow excursion into this topic, which was at the time when when I was at IU for the first time as a postdoc, I was both Santiago and Alessandro's, where I made my first visible contribution in this area. And after that, basically, I've been consistently producing work in this topic, which has to do with the optimization method, with a class of clustering techniques which consist of optimizing a function, a benefit function or quality function, specifically modularity by Newman and Girvan. The second one, which has been perhaps more consistently in my thread over this 15 years plus of activity in this area, is about the issue of validation. How do you compare to techniques with each other? Which networks do you have to use for that? What does it mean for a method to be better than another one? So this is, of course, an ill-defined question for an ill-defined problem, but there is a growing consensus about things which make sense. And I'm going to tell you something about this and how I contributed to address partly this question. And finally, which is something that takes me more to more recent times, literally the last few years, I'm going to discuss post-processing techniques. How do you clean up some noise out of the outcomes, of the usually noisy outcomes delivered by a clustering algorithm? So let me start with big thanks to all the people that have been involved in this activity of mine over the last 15 years in various phases, in various, of course, contributions. So I thank all of them. I want to make sure I didn't forget anybody. I put all the pictures here. You may recognize some of them. And let me go to topic number one. So one way to assess this problem, the most dominant way even today, is to assign a function that gives a score to the partition, and then looking, by doing an optimization, optimizing that measure by looking for the partition that gives the largest value of the largest or the smallest, not depending on what the meaning of this function, the optimum of the function in the space of the partitions. We call it global optimization in a way which is, I don't want to upset any expert of optimization out there. We don't refer to particular properties of the function, but just on the fact that this is an optimization on a function which expresses a score for the partition, for the whole division of the network, as opposed to local optimization, which refers more to an equivalent measure of goodness for the clusters individually. So clusters would be like more local, and the whole partition, so the whole division of the network into clusters or communities would be the global thing. So just to make sure I don't want to pick up a fight, with optimization people. That's what we mean by that. So you have a function, and then you look the partition that gives you, let's say, the maximum of the function. We're going to specifically talking about a function which maximizes, whose maximization is meaningful. Actually, even the minimization is meaningful, but we're going to focus on the maximization. There is a problem, a conceptual problem with this. I mean, which is the more serious, the more fixated you are on a specific demands that you make from your partition, what your partition should look like. So let me tell you what I mean by that. So suppose that I have a network, and I look and I optimize my quality function here. Suppose I find the maximum, and I find the partition that gives me the maximum, and I get these three clusters. And suppose that I find out, or actually I knew it all along, that this network I was working on is just a piece of a much larger network that was out of reach because of problems with the data, unavailability or not sufficient funding to cover, to be able to do a more exhaustive sampling of the system. So if I then look for the maximum, say the optimum, say the maximum of my function over this extended system, in general, I'm not going to recover the same clusters I found in the subset that used to be the whole network when I was doing it. So if you optimize the very same function on a much larger system than locally, I may not recover the same sub-partition that I got by optimizing the measure only on the subset. So this is a problem for people like me who are more inclined to think that communities are more like local structure, mesoscopic in fact, such that a piece of the network should not really, of course, perhaps for biology it's more difficult to believe that, because everything is part of everything, but you cannot just take the heart out of the body and then expect that the rest of the body functions like normally, obviously. But in general, if you think about broadly about communities, the idea is that you have this small portion of the network, and that somehow this portion of the network affects and is affected basically by a more regional portion of the network itself, and not by the whole thing. So that once you consider some extended neighborhood of that cluster, say, or the whole system, they should not change the classification of those nodes. But this is an open debate, so I don't expect people necessarily buy my line, or I totally accept different versions of this. So let me go down to the meat of this. In 2004, in one of the most cited papers in not just in community detection but in all of network science, Mark Newman and Michel Girvan introduced this function, Q, modularity. I'm going to tell you what it does, how to define it, what this the meaning of these terms is, and right after that, Mark Newman put this basically at the center of the universe of clustering algorithm. And almost 20 years later, this function is still at the center of the universe of clustering algorithm, despite all the progress and some of the things that I'm going to tell you. In fact, I think we learn more from this object than from anything else that's ever been introduced in this area. So we should be very grateful to Mark Newman and Michel Girvan for introducing this function, to Mark Newman for working extensively on ways to optimize this function and other insights that this function can provide. I tend to consider this equation, if you want, is a definition. It's not an equation. As important as this other equation is for physics. And I like to joke around saying that there are some formal analogies between these two expressions. If you think that, there is the m, there is the c, there is the square, but it is just joking around. The goal is to optimize this function. So this function has a clear upper bound and a non-trivial maximum, pretty much always. So it makes sense to look for the partition which allows this function to reach its maximum value. that was the beginning, the birth certificate of modularity maximization, this second paper. The first one defined the measure, the second one just put it, say, no, let's optimize this measure and forget about everything else. Like all interesting problems in optimization, this is an NP-complete problem. So there is a good chance that we will never find out, in a short time what the absolute maximum of Q is. It has a very rough landscape over the space of a possible partition. It's easy to bump into suboptimal solutions. It can also be actually very close to the actual maximum. And this has generated, was the reason why there's been a huge number of techniques, various techniques that approximate this optimization. They try to find some approximate solutions to this problem, to the maximum. So let me tell you what this thing means, actually. So this is a sum over the number of clusters. So for each cluster, you compute this difference, and then you divide by the total number of links, m. M is the total number of edges or links of your network. For each cluster of the partitions, you have a given division of your network into communities. For each community, you just compute this difference. The first term is the number of links inside the community. That would be, for instance, the number of green lines here, connecting, or blue lines, I don't know, it depends, it looks like green to me, connecting the nodes inside this oval here, or red lines, if you're considering the other clusters, connecting the red dots here. And then you subtract from this a baseline, which is the square of the degree of the nodes of the same group. So if you take, for instance, this group here is the sum of the degrees. The degree is the number of neighbors of a node. So for instance, for this guy would be 4. You take 4 plus whatever, how many neighbors this guy has, and so on. You do it for all the nodes. This gives you the total degree of the nodes of the cluster. You square this, you divide by 4m, m being again the number of edges of the network. So this is how you operationally define it. And the meaning of this is that you try to compare the number of edges that you have within the groups with the number of edges that you would expect to have within the groups if the network were randomized and links can be placed at random between any two nodes. Because you expect, of course, that there are always going to be links connecting nodes of a cluster, even if it's not a real cluster. So in order to define it as a cluster, you want that the actual number of edges is bigger than this baseline, significantly larger than this baseline. So that's what this difference indicates. If LC is considerably bigger than this baseline, then the group is probably a cluster. So it has a density of edges inside, which is larger than the baseline, significantly larger than the baseline. And then, of course, you sum over all the clusters. So for instance, the baseline is the traditional baseline. There you can choose different null models, but the traditional baseline, which is actually the one indirectly represented by this null model term here, is a so-called configuration model, in which basically I randomize my network by breaking all the links, so dividing them in this bunch of stubs, which are half links, and then I combine pairs of these stubs at random, so that at the end I know that number of links is the same and that each node preserves its degree as the same number of neighbors before and after transformation. If I do that, I can get, for instance, a network like this, in which you see now that the number of links connecting nodes of the same color here is much lower than at the beginning. So this term here is an average of the number of blue lines that I find within the green group, the blue group, and the number of blue lines that I find within the red group. It's very easy actually to come up to this expression. So you have a baseline, and as long as you are significantly above the baseline, then basically that means that the more different you are, the higher you are with respect to the baseline, the more modular your partition is, and therefore your network is. And you have to find the maximum of this quantity. The first contribution I brought to this area was actually when I was a postdoc here under Santiago and Alessandro, almost by chance, was to realize that there is some sort of intrinsic scale inside this function. This is the same function you've seen before, just written differently. I didn't change anything otherwise. But I do it so that you can see that basically there is some sort of hidden scale here, which is represented by the square root of the number of edges. This is what I like to call the modularity scale. And I don't tell you how, how we came to this result. It's actually very simple algebra. There is nothing more than that. But the presence of the scale here, with respect to which, for instance, the degree is measured because of this ratio here, as a consequence, the fact that clusters smaller than this scale, so cluster whose total degree is of the order of square root of m or lower or smaller, cannot be resolved by this measure, because the measure will tend to favor aggregations of these smaller groups into larger ones, such that you can go above this scale. So what does that mean, for instance, as a consequence? This is an example that we actually developed right here, and it's in the paper. So right here at IU, and that age, very far away from now. So this kind of Ringo clique, which has been used also afterwards, to see if other methods have the same problem. So basically, this is the most modular network you can imagine in many ways, right? You have these very, very tightly connected modules. So you see any two nodes are connected. Inside these are cliques, in this case, 5 cliques. And yet connected to each other by the fewest possible number of edges. They're basically forming this ring-like structure, and consecutive modules are connected just by one link. In a situation like this, you would expect that any method would tell you naturally that each of these cliques is an independent community. However, I mean, this is specific for this case, but there are of course different arrangements. You find that modularity is higher if you consider grouping these cliques in pairs or triples, depending on the relative size in terms of degree of this clusters or unions of clusters with respect to the square root of m, this scale. But you say that why would I care about a toy model like this? I'm not going to find networks like this in the real world. That's true. So what you should really be worried about in general, if you just apply and you find the modularity maximum, I just don't mean an approximation of the maximum. This is a problem somehow of the measure itself. So suppose that you find the exact maximum of the measure, no matter with which method you're using to get to that result, and you have a network you've never seen before, and some of the clusters of your partition, in this case, maximum modularity partition, have a degree which is of the order of square root of m or smaller, you can never tell a priori if this cluster here looks like this, so it's more compact, cohesive group, or if it's a combination of smaller clusters, because in both cases, a modularity will tend to put everything together to bypass, to go higher than this scale. It's really like we call it resolution limits, because it's really like, I don't know, perhaps some of you are, or many of you are biologists in the audience today. So, it's really literally like a microscope that you can really see, under below a certain scale. And of course, the larger the network, the more serious this problem is, because then the square root of m grows, and then there may be meaningful modules under the scale that would be invisible to modularity in many situations. So this came out when I was still here as a postdoc in those golden age. Right now, I met Santiago and the other guys had a lot of fun here at IU, and that was somehow when I decided to dedicate a consistent, a fair amount of my time to this activity, because then I thought, okay, if there is this issue, of course, we have to try to bypass it, to solve it, and that led actually a number of people to the development of so-called multi-resolution method, in which you introduce, for instance, in this case, just a parameter here, gamma, which you can tune so that you can effectively change the resolution, literally like you're taking a microscope, tuning the resolution of your system. And some of these methods are still very popular today. But overall, it made people question whether this was really the best way to do the job. And more recently, there is a lot of growing attention towards statistical inference techniques that they have a number of benefits with respect to modularity, but also share a number of affinities with it. I'm not talking about this now. Let me go to the second point that I want to make, which is about validation. So how do you test clustering algorithm? This is, again, of course, it's an ill-defined problem, and this is the $1 million question, because if I knew how to tell whether a method is better than another one, I would have an objective criterion to keep pursuing the winner-take-all method. Of course, there is nothing of the kind. So what we can do, we can start to think about ground truth-like artificial networks that resemble what we expect to recover in real settings. So normally what we do, we have a class or multiple classes of artificial, so toy model networks, which have built-in classes there that your technique or your techniques are supposed to recover. And by far, the dominant class of models, the generate benchmark for testing clustering algorithm is stochastic block models, concept originally introduced by Holland et al. and very popular in these days. So stochastic block model is basically a model of network, a random network, which is modular in that basically the probability the two nodes are connected depend on their membership. So on the left here, you see what is called a stochastic block matrix, which tells you basically the square, and the size of the square tells you the probability that nodes in the same block that would be in the diagonal. So this would be the probability that nodes of the first block, probability that nodes of the second block, and so on. There are 6 blocks here are connected. And the blocks outside of the diagonal tells you what is the probability that nodes of different blocks are connected. So you see, you can have a variety of scenarios where the classic scenario that I tried to depict so far of assortative communities would correspond to a situation in which this matrix has big elements on the diagonal and very small elements outside of the diagonal, comparatively smaller elements, because you have basically high density of linking inside, high probability of linking within the clusters, and lower probability of linking outside. But this setting is more versatile because it allows you to consider different scenarios. Also, when you have strong links between different groups, then you can recover these assortative communities, so core periphery structure, all these things at the same time. So specifically in the literature, people have been using a version of this simplified version, subclass of stochastic block models, which is called the planted departition model, originally introduced by Condon and Karp in 1999. The versions of it were actually already out there before then. And this is a very special version in which you have only 2 probability of forming links. One probability P tells you how likely it is for 2 nodes in the same group to be connected, and the other probability of parameter Q that tells you how likely it is for 2 nodes of different groups to be connected. So you see here in this diagram, here I emphasize a node inside this red group with a probability P that is connected to the other nodes of the red group, and a probability Q that is connected to all the other nodes outside the red group. And the principle is that if P is bigger than Q, the groups are assortative communities, because basically means that there is a higher chance for nodes of the same group to be connected than for nodes of different groups to be connected, just because the probability is larger in the first case and not in the second, than in the second. This very simple approach that has been used for like at least a decade until this development I'm going to introduce now, had a couple of limitations. Limitation when you think about the realistic networks that you want to actually apply your algorithm on. And the limitations are the fact that, as you may have noticed before, clusters actually, at least in the standard version of this model, but in principle you can refine it, are usually of the same size, which is unrealistic. And also, by construction, in this network, all the nodes have the same number of neighbors, approximately. Both these features are not realistic. We know, of course, in real networks, the clusters can have very significantly different sizes, and nodes have a broad distribution of degree. So what we did in 2008, we introduced a refinement, a modification of this model, which is now called, from our initials, the LFR model, or the LFR benchmark, which consists in introducing this heterogeneity, realistic heterogeneity, into these model graphs. So as you see, this is a snapshot of an LFR network in which you can see that nodes, the groups have different sizes. Groups are identified by the color, and the size of each node indicated by the balls here is proportional to its degree. So you can tell from the size that there is a significant difference in degree. Some nodes have a lot of links, a lot of connections. Some nodes do not have many connections, resembling somehow much more closely, of course, than the original planted partition model, a situation that we encounter in our daily operations. So this is the paper, and actually more recently, NetworkX, a popular library of network science tools, has created its own function to model, to generate LFR graphs that you can get from there. It's not really perfect so far, so I'm not really happy about it. Crashes very often, it's not really scalable, but at least it acknowledges the status that this model has received, acquired over the years. And after we created this tool, we immediately applied popular techniques of that time, when we did that, talking about more than 10 years ago, on this benchmark to see really, which method to challenge, more methods, really more than it has been done until that time, because of this heterogeneity, to see which role heterogeneity plays in the performance of this method. So this is the list of methods we consider, 12 of them. This is basically the authors. This is the label that I'm going to see in the next plots. And this is some information about their complexity, computational complexity. N is number of nodes, M is number of edges. And then there may be some parameters. Sometimes the complexity is parameter dependent. In most cases, it's usually some function N and M. We're talking really about ages ago, but this paper, this comparative analysis of 2009 with Andrea Lancichinetti, that time was a PhD student, has attracted a lot of attention then. There were different classes of method here. This is about, for instance, so-called bridge separation, bridge deletion, in which you recover the classes because you are removing the links between them until basically you free them, you separate them from each other. These other three techniques are about different ways to optimize modularity. Now you know what modularity is. These different techniques use random walks to find the clusters. It's just a broad kind of overview of the type of methods that you can find to discover clusters. But of course, it was not exhaustive, and now there are literally hundreds of techniques. But they were actually the most representative back then. At the same time, we needed techniques that had a code available that was easily to reproduce, that we could also create it on our own. And that's why at the end we stick to that list of 12. And each of these methods leads to one of these diagrams here, where we show the performance of each of these methods on the LFR benchmark graphs. And on the x-axis, we put the degree of mixture of these clusters. Basically, when mu t is close to 0, it means that the clusters are almost separated. There are not many links between them. As you increase mu t, then there are more and more links connecting these groups until eventually they are all blended and it's difficult to distinguish them. So the question is that, when you start missing and misclassifying groups, and when the groups start to become invisible, on the y-axis, we measure the similarity between the planted partition of the model and the recovered partition, the detected partition from the method. And we use a normalized mutual information for that, which is a number between 0 and 1. So of course, at the beginning, we have perfect performance, and then of course, performance degrades. The 4 different lines correspond to different settings, different choices of sizes of the benchmark. You see 1,000, 5,000 nodes, and also what we call the small communities and big communities, small communities being a range of community sizes from 10 to 50 nodes, big communities, a range of community sizes between 20 and 100 nodes. Because we wanted also to see how much the heterogeneity in cluster size distribution plays a role. And you can see here from the fact that sometimes the curves are very different, that both the size of the network and the heterogeneity in the cluster size play a role. And you can, of course, see it for yourself. Slides will be available. But the take-home message at the end of this analysis that there were 2 methods that were clearly standing up, and the InfoMap and the Louvain method. But I put an asterisk here. Louvain algorithm is probably the most used algorithm today, but I put an asterisk here to clarify what it means that this method was excellent somehow, among the best of this analysis. Whereas the other modularity optimization techniques, like for instance, this one and this one, were so poorly performing in the setting that you may expect large networks, small cluster size, because of the resolution limit that I told you before, because of this inability of the measure when optimized to recognize small groups. I say, why don't you have this problem here? I mean, you still have it to some degree, but it's mitigated by the fact that we did not use the outcome of the algorithm corresponding to the best model, to the high modularity partition. This algorithm has a specific feature that it proceeds in a hierarchical fashion. So it finds basically different levels of aggregation with small clusters at the beginning that become larger and larger, and then eventually it reaches the partition with the largest modularity. We did not take that level, which is the one that everybody takes when they apply the Louvain algorithm today. We took the low level, the one with the smallest cluster. This is the one leading to this curve before that you've seen before, to this excellent performance on our benchmark. We didn't make it clear in our work, so people started using the Louvain algorithm. It's very popular today, but this limitation is there. If you use the actual highest modularity partition that is delivered by the method, then the performance degrades and becomes, as you see here, these are the same 4 networks, 4 classes of networks of the plots that you've seen before, and we compare here what happens if you take the lowest level, good performance, is the one you've seen earlier. Whereas if you obtain the highest modularity partition, then you get significantly degrading performance. You see how bad it is when the network is large and the communities are small. So this Diamonds here are the one that people are using today. You know, when this, the ones that you get, you know, if you didn't know about this problem, this would be the answer that the method gives you. So there are good reasons to be skeptical about it. So take a look at that. Be careful. One last thing I wanted to talk about, this that we introduced in the context of this analysis was the so-called negative test. I mean, if you have a good method, you should not find clusters where there are no clusters, right? So these are 10 diagrams because for two methods, you know, the analysis would have taken too long. They were kind of slow. So we included only the 10 fastest one. This tells you how many clusters you find in completely random network, scale-free with the power law degree distribution or with Erdős-Rényi standard Poissonian distribution. You see that instead of finding like one cluster, including everything, or as many clusters as there are nodes, so partition into individual nodes, which would be acceptable answers. When the network is very sparse, you can easily find, even for, you know, from InfoMap and this, they called at the time Blondel et al., now it's called Lubena algorithm, you can still find non-trivial aggregation of nodes, which are in principle meaningless because they shouldn't be there. These networks are random. So as an additional piece of advice to you, when you develop a new method, or you know, if you are playing with a method that you like, just make sure it doesn't find, you know, signal where there is no signal. So feed in with some random graphs and see if you still find structure there. If it finds it, there is something that you should be careful about when you actually apply your method on a real data and you want to extract answers from that data set. Okay, last thing I wanted to talk about is about post-processing techniques. This method I talked about, you know, mostly optimization techniques like modularity maximization. They are stochastic, which means basically if you change your random number sequence, the random seed, basically they're going to give you slightly different answers, or sometimes they're actually significantly different answers. So just like when you make a measurement. But what does it mean to have noise in partitions when the outcome is a partition? So this is an example. This is a famous Zacchary's Karate Club, real network just being used as a benchmark gazillions of times. Actually, it's probably mostly cited because of that and for any other reason. And these are two different outputs of InfoMap. One of these methods is seen before, is also fairly popular today, was also one of the best performing methods in our benchmark. Two different, you know, outputs of InfoMap on this very same data set if you use different random seeds. So you see, in one case I get 3 networks, in one case I get 4. So which one shall I go for, 3 or 4? So how do you settle, you know, for a situation like this? I mean, it can look like I'm fooling you because I'm cheating, because in principle, for instance, even InfoMap is an optimization technique. It optimizes, actually minimizes what is called description length of a random walk. So in principle, say, okay, I have different answers that I can get, slightly different or significantly different, like in the case before, but I have an objective criterion to tell which one is better than the other one. You know, the one, for instance, in the case of InfoMap, who gives me the lower description length. So that would be case closed. But the question that I'm gonna, and that actually would be a good way to address this criticism and say, you know, you shouldn't care, right? You take, you know, you run the method many times, and eventually you pick the one corresponding to the largest or the smallest value of your quality function, depending on what you're trying to do, if you're trying to maximize it or minimize it. But instead of doing that, the question is that, I mean, can I use the suboptimal partition to improve the final result? So also the partition that I would disregard because they're not as optimal as others that I find in my sample. And that's the thing that you try to address, and it's become very popular today. And of course, it's been under scrutiny with different works, including like in the last year. I call it post-processing technique, and of course, it's one of different things you can try to do. It is known as consensus or ensemble clustering. Ensemble clustering, consensus clustering was introduced, as far as I know, in this paper 2002 by computer scientists. Very nice work. Mostly, you know, in the context of data clustering, but of course the principle is the same. Once you have different partitions of objects, in our case, the nodes of a graph, but it can be anything, then how can I average over them to get an improved result? Just like you do when you measure when you average different measurements of the same object, you know, in different settings. What you do, so the goal would be to search for the partition which is most similar on average to the input partition. This is how I rephrase this. This is called the median or consensus partition. So, and the similarity can be measured by different ways, for instance, by using normalized mutual information. But it is a difficult combinatorial optimization task. So you cannot really do it exactly as it is formulated. You have to do it in some sort of approximate way. And there is a greedy solution, which is the one that we embrace, which consists in using what is called consensus matrix. What is a consensus matrix? Once you have a bunch of partitions, it's a partition whose entry, ij, dij, is the frequency that nodes I and j are in the same cluster in the input partition. Basically, it tells you how many times I and j were co-clustered. That's why it's also called co-clustering matrix. So you have 100 partitions, you check how many times I and j were co-clustered. If they were, say, co-clustered 50 times, you divide by 100, you get 1/2. That would be that element. And this is the paper where we use this object in a recursive way by following this very basic scheme. I spare you the details. Of course, we can discuss offline, or can have separate conversations about this. So basically what you do, you get your favorite clustering algorithm, which of course has to be stochastic. So you apply it a number of times on your data set. And you get the consensus matrix, so those partitions, and then you reapply your method on the consensus matrix by treating the consensus matrix as a new network. And then you get, again, a bunch of partitions, you get a new consensus matrix, and you keep applying this until you converge to a matrix which becomes a block diagonal. Eventually, this is exactly what's going to happen. So basically, it becomes disconnected, and then the groups, the blocks of your matrix are your communities. So just to give an example of the power, the potential power of this technique, I take this very plain situation here in which I have what seems to be an obvious partition in two communities indicated by these two different colors. And I have 4 different input partitions, including 2 quite wrong ones. So 2 are the correct ones, and the other 2 are wrong because there is another group. They're indicated by the green diamonds. If I create a consensus matrix of all of this just the same way, I get this thing. The equivalent graph of the consensus matrix is, of course, weighted now because the elements are not just 0, 1. In this case, actually, we have 4 different values, 4, 5, including 0, but say 4 different non-zero values for these elements. 1, when both nodes are always co-clustered, like for instance, these 2 blue nodes, they're always co-clustered, they're always in the same color in all 4 input partitions. And then all the other situations here. So you see what happens basically that in the equivalent weighted graph or the consensus matrix, I made the links between the communities, the actual communities, stronger, whereas I weakened the bridges between them. As I apply recursively this technique, what happens is at the end, these bridges will disappear, they will become very, very irrelevant. And then these links, internal links, will become stronger and stronger. That's exactly what eventually leads to the breakup of the network into your partition. By doing that, we get actually very, very good results that improve over the results of applying directly the method on your data set. So without doing a post-processing consensus clustering analysis. And actually, I want to show specifically this for different methods and different network sizes. For different methods, 2 different network sizes. I would like to emphasize specifically the performance of this technique here. This is a greedy method to optimize modularity. So now you know what modularity is. Which you see, if you apply it directly on your network, the networks are still our LFR benchmark graphs. You get this very poor performance that you see in the previous diagrams. But if you do consensus clustering, then you basically, there is a way to use these different inputs, this very different partition to get something meaningful, much closer to the ground truth. Especially here, when the network is even bigger, sometimes you even get exactly the right partition by using consensus clustering, whereas you get very far, you stay very far from it if you just are happy with the result of the application of your method on a data set. Okay, the last thing I wanted to say is that there is a problem with time complexity about this technique, because constructing a consensus matrix means computing the n-square elements of the consensus matrix, which means that then you have a worst case complexity of O(n) square, which is not what you want, because this way you cannot really analyze large graph. And very recently, just 2 years ago, we published a paper that solves this problem, mitigates this problem by not computing all elements of the consensus matrix, but just sampling them. Basically considering mostly the elements of the consensus matrix only between pairs of nodes which are neighbors. You do not consider nodes which are not neighbors. And this way you can bring the complexity down to O(n). This is the paper. Okay, let me summarize. I discussed 3 things here. Problems of global optimization techniques. So you should be aware of their biases and possibly of the way that, tricks that people use to go around them. You should always be very careful about validation, what it means that you're using a clustering algorithm you can rely on, how the validation was done, That doesn't necessarily mean to embrace our algorithm, our LFR benchmark, and use something else as long as it's reasonable, but that's to pay attention to that, especially also try to make sure that your network does not find clusters in random graphs, because that would be disappointing and could also be dangerous if you apply it then on real data sets. And finally, consensus clustering seems to be an effective post-processing technique to clean up some noise from your partitions and get you more clear results. At the end, I point you to this link here of my website, where you can find the code for some of the things that I described today, from our consensus clustering, slow and fast techniques, to the LFR benchmark, to other things. And then this is the paper that Santiago mentioned in his introduction. It's kind of considered by many. In fact, I should have upgraded the number of citations. It's close to 10,000 now, according to Google Scholar. And this is actually a more recent review that I've written, because this topic is evolving so fast that it's really difficult to keep track of everything which was going on. This is mostly about a discussion about the principles. It's not as exhaustive as the other one, so the two works are complementary. So please cite them both if you mention them. I also would like to advertise our recently published book, introductory, very introductory, probably the easiest way to access network science if you don't have a technical background. It's a software-based code, it's Python, a software-based introduction, so with a lot of code in Python using NetworkX library. But the concepts are very simple. Formulas are really used to a minimum degree, and so I encourage you to use it. For people, I don't know, perhaps or with biology, so economics management. All this for undergrad, it seems to be just the right thing to use. For graduate students, of course, if you expect something more technical, this is not a book for you. But if you have a mixed audience, perhaps it's a good idea to use the book and the resources attached to the book. Like, for instance, our free tutorials that you find at this GitHub website from Cambridge. These are freely accessible. Each chapter is its own tutorial that teaches your student how to analyze a graph and model graphs. And the last thing is what Santiago said. I'm the chair of Networks 2021, possibly the largest ever event in network science. It's the first historic merger of Sunbelt and NetSci conference, which have always been held separately. They're different communities, but we all deal with graphs, so we try this experiment of putting them all together. It's going to be in July. Unfortunately, in a virtual format. We just decided to do that for the reasons you can imagine, but that does not make it less intriguing and interesting. So I advise you to take a look at the website and possibly register for that. With that, I can take your question. Thanks a lot.
Thank you, Santos. So we really appreciate that you have taken the time to give this talk. And I'll now open the floor to the participants of the seminar. Well, if there are not any questions, so just out of curiosity, so and this is probably more epistemological than actually scientific, the question. Mm-hmm. So the way you are describing the communities is in a static manner. So how much do you think that the static representation of the network actually represents on reality what a network of communities could be in reality when people are moving around, changing space and time, and whether there has been research done on that area?
Yeah, of course, I didn't touch upon this. This is such a big area. This is what would be called dynamic clustering, right? When you search for classes in a dynamic environment. In fact, as you know, basically all networks are dynamic, right? Even they have their own scale. Sometimes the scale is very quick. If you take, I don't know, a network of Twitter users retweeting each other posts, then you have a dynamics which runs of the order of minutes. In minutes, you can make cascades of things. Where if you take biological system, it can take a much longer scale. You need, mutations, some generation, evolution, and so on. But all the systems are dynamics. Yes, of course. A lot of the concepts I mentioned today are easily extendable to the case of dynamic networks. This is a very active area. In fact, especially in the last 10 years, people have been focusing on that domain just for the reasons you mentioned, because of course you cannot underestimate the importance of this. Specifically, it's an example that I like to make, and of course I didn't have the time to make it today. You can use consensus also to make a better sense of the stable cores within communities over time. Because what you do then, you just take your system, the history of your system, you divide it into snapshots, and you find the communities in some sort of static snapshots, and then you use consensus to put them all together and see if there are some stable portions of these classes which are stable, which basically been the same all the time. So it can also help you to extract the static cores. Just an example of things that I introduced today that can be adapted to that environment. But there are certainly ways, and I don't think that I can mention too much about this today. People are totally aware of this. I'm writing actually a book on the network communities starting years ago. I hope to finish this year. There is a specific chapter about dynamic clustering. So clustering of clustering of networks or dynamic networks. It's a big deal because there are things that one has to take into account. And usually one thing which is very common in this case is to take advantage of the so-called multi-layer representation of network, indicating where each layer represents a different moment in the evolution of the system, significant moment, which also means that you have to be smart to identify a good way to slice your time horizon so that you have enough information in each slice. But there are also ways to include the whole temporal evolution by considering the network as a single item. Specifically, there are ways, for instance, to extend modularity to the temporal case, and statistical inference techniques, for instance, inferring stochastic block models in multi-layer temporal networks are also kind of fashionable today. So that's a very good question. I mean, yeah, people are totally aware of this. And in fact, actually, I still have to write the chapter. It's going to be one of my summer tasks. And so I'm sure that I'll find out more stuff than what I'm already aware of when I put all the sources together.
Thank you.
Thanks to you, Santiago.
So any questions from the students, the group? Don't be shy.
Yeah, that's probably the reason. You can write it in the chat, if you don't want to show your face. And of course, you can also reach out to me after this. If you have special interest, I'm always happy to talk about this stuff.
Hi, Santo. So actually I had a question.
Yeah.
So, and first, thank you for the great talk. So I study computational social sciences and especially social networks in Twitter. And so in these cases, usually I see there's a lot of metadata that can be used along with the edges themselves. And have you done like some work on like how to make good use of those metadata, like their communities as well?
Yes. This is a great question. And to be honest, 10 years ago, one could only conceive this question because they say, I don't really have so much information about attributes, right? I only have, and to be honest, I mean, I'm a kind of old-fashioned person. Of course, I try to keep up with new things because otherwise, you can easily be marginalized no matter what you did in the past. So I still like very much to focus on the problem in which all you have is structure. But I guess even a survey, which was published, in fact, even before I moved to IU, so it's now, which is really covers a tiny portion because so much more came after that, or how to integrate structure with non-structural information attributes. Specifically, actually, I published a paper a few years ago, which pissed a lot of people off. Santiago actually and I are very similar in that we really like to piss our colleagues off. I had promised to publish a paper because one of the referees said at some point, what are you kind of trying to say? That what we did was useless, including what you yourself did, which you being me. That paper was basically saying, we take techniques which have been developed in the context of structure alone, pretty much everything that you've been hearing about in the last hour, and a few more things. And then I see how similar the structural communities are to communities of metadata. So when I have this information. So social circles within, like things like journal, they have actually their own communities there, which are human evaluated, if you want, or even book clubs or things like this, or even there are different settings in which this information is available. And actually, a lot of these data sets are available in Stanford SNAP library, and we took many of them from there, and then we created a couple of data sets, and we show how poor this match was at the end. So that, and then I didn't want just to shock people or anything to say that, because the fact that it works so well when you use structure alone does not mean that automatically does not translate in a great performance when you try to recover attributes or use structure to recover attributes that you don't have. So that was what started this. And actually right away after that, somebody who lives very close to where you're now, Mark Newman, actually wrote to me right after the thing came out to say, this is actually, I'm very intrigued by this discrepancy. I would like to study it. And he proposed a stochastic plot model that included also not attributes. At the same time, while I was thinking to do the exact same thing with another colleague of mine, Tiago Pessoa. So now there were at least 2 papers that came out, and then another one, and then others. So basically, it's possible, for instance, there are frameworks which are flexible enough to account for the coexistence and the usage of both structural and metadata input. So this is really very recent stuff. We're talking really about the last 5 years. So I expect more evolution. And to be honest, if there is something you're young and you can perhaps also develop your own independent line of research, one thing that I see very promising in an area in which deep learning is basically pervading our lives is to use embedding techniques to embed a network using both structure. So basically graph embedding techniques that use both structural, so basically the position of the nodes based on how close they are to each other, and their own attributes. In my opinion, this is, I mean, I have this feeling, but I'm investigating this even as we speak, and probably other people too. I have the feeling this is the best ways to use embeddings to recover clustering. We just published something showing that embeddings in pure structure are not that great 3 days ago, literally. So the next step is, how can we improve over this? Do we need to change something about the way we embed structure, or do we have to integrate the information with non-structural attributes? So this is totally new, which means that you can play a role in that. I don't know exactly what you're interested in. If you just want to use a method because you're more interested in the specific social phenomenon, is one thing. That's not really what you should do. But we're talking really literally about papers of the last couple of years. So this is, people are very aware of this. And I actually personally played a role in this a couple of years ago. And like I said, pissed people off. But now people are aware of the fact that you cannot really treat these things in separation, that sometimes attributes can help you even to recover structural communities better. So it's an input that you cannot underestimate. You cannot just put it under the rug because you don't know. Some framework, like for instance, modularity, they're not flexible enough to account for this. You will have to substantially modify it to include also this type of input, because it was meant, talking about 20 years ago now, as a measure which holds only for structural, information. But now we have framework, we have statistical inference, we have embeddings that can put all these things together. So these things is out there, and we're just testing them even as we speak. Thanks for your question. It's very important, very timely.
Thank you for the answer.
And we can follow up. You can also write to me after that. I can stick around much longer today, as you can imagine. Neither can you, probably. But there are always emails. There are always other options.
Sure.
Any other questions? Well, if not, so let's thank Santo again. So we really appreciate the chance that you have given us to hear your presentation. So
thank you, guys.
Thank you.